Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How gravity bends light in space. Light travels in straight lines through empty space. Or at least, that's what our everyday experience suggests. A laser beam shoots across a room in a perfectly straight path. Starlight reaches Earth from distant stars without deviating from its course. But this intuition breaks down when gravity becomes involved. In the presence of massive objects, light follows curved paths, bending around stars, galaxies, and even clusters of galaxies in ways that reveal one of the most profound insights about the nature of space, time, and gravity itself. The story begins with Albert Einstein's general theory of relativity, published in 1915, which fundamentally reimagined what gravity is. Newton had described gravity as a force. Masses attract each other across distance through some invisible pull. Einstein proposed something radically different. Gravity, he suggested, is not a force at all, but rather a consequence of the geometry of space-time itself. Massive objects don't pull on other objects. Instead, they warp the fabric of space-time around them, and objects simply follow the straightest possible paths through this curved geometry. Imagine space-time as a stretched rubber sheet. Place a bowling ball on the sheet, and it creates a depression, warping the flat surface into a curved shape. Now roll a marble across the sheet near the bowling ball. The marble's path curves as it moves through the depression, not because the bowling ball is pulling on it, but because the surface itself is curved. The marble is still following the straightest path it can, what mathematicians call a geodesic, but in curved space, straight lines look curved to outside observers. This is what happens with light near massive objects. The light is following a geodesic through space-time, travelling along the straightest possible path. But because space-time itself is curved by the presence of mass, that path appears curved when viewed from our perspective. The light isn't being pulled by gravity in the Newtonian sense. It's simply following the geometry of space-time, which has been warped by mass. The amount of bending depends on two factors: the mass of the object doing the bending and how close the light passes to that mass. More massive objects create deeper curves in space-time, causing more dramatic bending. Light passing closer to a mass experiences stronger curvature than light passing farther away. For most objects we encounter in daily life, this bending is utterly negligible, far too small to detect. Even for something as massive as Earth, the bending of light is minuscule. A beam of light grazing Earth's surface would bend by less than 1,000th of a degree. But consider the Sun. With a mass 333,000 times greater than Earth, the Sun creates a significant warp in space-time around it. Light from a distant star passing close to the Sun's surface is deflected by about 1.75 arc seconds, a tiny angle equal to roughly the width of a quarter viewed from 2 miles away, but measurable with careful observations. This prediction of general relativity was first confirmed during a solar eclipse in 1919, when stars near the Sun's position in the sky appeared slightly displaced from their normal locations. The Sun's gravity had bent their light as it passed by, making the stars appear to be in slightly different positions than they actually were. This gravitational bending of light becomes dramatically more pronounced around more massive and compact objects. A neutron star, containing more mass than the Sun, compressed into a sphere only about 12 miles across, creates such severe space-time curvature that light from the far side of the star can bend around it and reach an observer on the opposite side. You could theoretically see more than half of the star's surface at once because light from behind curves around to the front. Black holes represent the extreme limit of gravitational light bending. At the event horizon of a black hole, space-time is curved so severely that light emitted outward from that surface is bent back inward. The escape velocity at the event horizon equals the speed of light, which is another way of saying that space-time curvature there is so extreme that even light following its straightest possible path still curves back toward the black hole. Just outside the event horizon, there's a region called the photon sphere, where light can orbit the black hole in unstable circular paths, bent continuously by the intense curvature of space-time. The shadow of a black hole, the dark region we see in images like the famous Event Horizon Telescope picture of M87's supermassive black hole, exists because of this extreme light bending. Light that passes close enough to the black hole is captured, unable to escape, creating a dark silhouette. The bright ring surrounding this shadow is light from the accretion disk that has been bent and focused by the black hole's gravity, with some photons having orbited partway around the black hole before reaching the observer, creating multiple images overlaid on each other. Gravitational lensing occurs when light from a distant object passes near a massive object on its way to Earth. The massive object acts as a lens, bending the light and focusing it toward Earth, just as a glass lens bends and focuses light. Galaxies and galaxy clusters containing hundreds of billions or even trillions of times the Sun's mass are particularly effective gravitational lenses. When a massive galaxy cluster lies between Earth and a more distant galaxy, the cluster's gravity bends light from the background galaxy, often creating multiple images, arcs, or even complete rings. Einstein predicted a specific case called an Einstein ring, which forms when the lensing mass, the background light source, and the observer are perfectly aligned. In this configuration, the background object's light is bent equally in all directions around the lensing mass, creating a circular ring of light. Perfect Einstein rings are rare because perfect alignment is unlikely, but numerous partial rings and arcs have been observed where the alignment is close but not exact. Strong gravitational lensing creates multiple images of the same background object. Light from the source can take different paths around the lensing mass, arriving at Earth from different directions. An observer sees the same galaxy or quasar in multiple locations in the sky simultaneously, each image distorted differently depending on the path the light took. By analysing these multiple images, their positions, brightness and distortions, astronomers can map out the distribution of mass in the lensing object, including the dark matter that can't be seen directly. One of the most famous examples of gravitational lensing revealed itself in the Hubble Deep Field images. A massive galaxy cluster acts as a natural telescope, magnifying and brightening galaxies far behind it. Some of the most distant galaxies ever observed were discovered this way, their light amplified by gravitational lensing to the point where even these incredibly faint, distant objects become visible. Without the magnification provided by the intervening cluster's gravity, these galaxies would be too faint to detect, even with our most powerful telescopes. Weak gravitational lensing is a more subtle effect. Rather than creating obvious multiple images or dramatic arcs, weak lensing slightly distorts the shapes of background galaxies. Each galaxy is stretched and sheared by a tiny amount, usually only a few percent. Individual distortions are impossible to distinguish from the galaxy's natural shapes, but by measuring the shapes of thousands or millions of galaxies and looking for statistical patterns in their distortions, astronomers can map out the distribution of matter, including dark matter, along the line of sight. This technique has become one of the most powerful tools for studying dark matter distribution in the universe. Gravitational lensing also affects the apparent brightness of objects. When a massive object passes between Earth and a more distant star, the foreground object's gravity can focus the background star's light, temporarily brightening it. This gravitational microlensing is used to detect exoplanets, When a star passes in front of another star, the foreground star's gravity creates a brief brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence even though the planet itself is far too faint to see directly. The time light takes to travel along different paths around a gravitational lens can vary. Light taking a longer path around one side of a lensing galaxy arrives later than light taking a shorter path around the other side. For variable sources like quasars, which change in brightness over time, this time delay becomes observable. A brightening in one image of a lensed quasar will appear days, weeks, or months before the same brightening appears in another image, the delay corresponding to the difference in light travel time along the different paths. Measuring these time delays allows astronomers to determine distances to the lensed objects and constrain cosmological parameters like the universe's expansion rate. Space-time curvature near massive objects doesn't just bend light spatially, it also affects light's frequency through gravitational redshift. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths and lower frequencies. Photons emitted from the surface of a white dwarf, neutron star, or near a black hole arrive at Earth redshifted compared to identical photons emitted far from any massive object. This gravitational redshift is distinct from the Doppler shift, caused by motion. It's a consequence of how time itself runs slower in stronger gravitational fields. The ability of gravity to bend light provides one of the most direct ways to test general relativity. Every observation of gravitational lensing confirms Einstein's predictions about how space-time curvature works. The precise angles at which light bends, the patterns of multiple images, the time delays between images, and the gravitational redshift all match the predictions of general relativity with remarkable accuracy. Alternative theories of gravity make different predictions, and so far, every test has vindicated Einstein's century-old theory. Gravitational lensing has become an essential astronomical tool. It allows us to study the distribution of dark matter by observing how it lenses background galaxies. It magnifies distant galaxies, enabling studies of the early universe that would otherwise be impossible. It reveals exoplanets orbiting distant stars. It measures cosmic distances and the expansion rate of the universe. All of this is possible because massive objects warp spacetime, and light faithfully follows the curves and valleys of that warped geometry. The universe is filled with matter, and that matter curves spacetime everywhere. Light from the most distant galaxies has travelled billions of years to reach Earth, passing countless galaxies, galaxy clusters, and vast expanses of dark matter along the way. Every massive structure the light passes deflects it slightly, creating a cosmic hall of mirrors where every photon's path is bent and redirected many times. The images we see in our telescopes are not straight-line projections from their sources, but rather the accumulated result of countless tiny deflections as light navigates the curved spacetime of our universe. The geometry of the universe itself, on the largest scales, also affects how light travels. If the universe has overall positive curvature, like the surface of a sphere, light paths will eventually converge. If it has negative curvature, like a saddle shape, light paths diverge. Current observations suggest the universe is nearly flat on the largest scales, meaning that, on average, over distances spanning billions of light years, light travels in straight lines. But locally, around every massive object from planets to galaxy superclusters, space-time curves, and light follows those curves, revealing the intimate connection between matter geometry and the paths that light traces through the cosmos. How we find planets around other stars. For most of human history, planets were only known to exist in our own solar system. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye, and with telescopes came the discoveries of Uranus and Neptune. But beyond our solar system, despite billions upon billions of stars filling the galaxy, no one had ever confirmed the existence of even a single planet orbiting another star. The problem wasn't that exoplanets, planets around other stars, didn't exist. The problem was that they're extraordinarily difficult to detect. A planet is tiny compared to its star, produces no light of its own, and sits right next to a brilliant star that outshines it completely. Trying to see a planet next to its star is like trying to spot a firefly hovering next to a searchlight from hundreds of miles away. The first confirmed exoplanet around a sun-like star was discovered in 1995 by Michel Mayor and Didier Queloz, who shared the Nobel Prize in Physics in 2019 for this groundbreaking work. They didn't actually see the planet. Instead, they detected its presence indirectly by observing how it affected its parent star. This indirect approach has proven to be the key to finding exoplanets, and astronomers have developed several clever techniques that reveal planets without ever actually imaging them directly. The method Mayor and Queloz used is called the radial velocity technique, sometimes known as the Doppler wobble method. The basic principle relies on the fact that a planet doesn't simply orbit its star. Rather, both the planet and the star orbit their common center of mass. Imagine two ice skaters holding hands and spinning around. If one skater is much heavier than the other, the heavy skater barely moves, while the light skater whips around in a large circle. But the heavy skater does move slightly, wobbling around their common center as they spin. The same happens with stars and planets. Jupiter, the most massive planet in our solar system, causes the Sun to wobble slightly as both orbit their common center of mass. The Sun's wobble is small. It shifts back and forth by only about 13 meters per second, roughly the speed of a bicycle. But this wobble is detectable. As the star moves toward Earth, its light gets slightly blue shifted, compressed to shorter wavelengths. As it moves away, the light gets red shifted, stretched to longer wavelengths. By measuring these tiny shifts in the star's spectrum with extremely precise instruments, astronomers can detect the wobble and infer that a planet must be causing it. The planet Mayor and Queloz discovered, orbiting a star called 51 Pegasi, created a much larger wobble than Jupiter creates in our Sun, because this planet is both massive and very close to its star. It completes an orbit in just over 4 days, compared to Jupiter's 12-year orbit. The close proximity and short period make the wobble more pronounced and easier to detect. This planet, later named Dimidium, shocked astronomers because it's a gas giant similar to Jupiter, but orbiting closer to its star than Mercury orbits our Sun. Before this discovery, most astronomers assumed that giant planets could only form far from their stars, where temperatures were cold enough for ice to exist. The discovery of hot Jupiters revolutionized our understanding of how planetary systems form and evolve. The radial velocity method works best for finding massive planets close to their stars because these create the largest wobbles. Small planets like Earth create wobbles so tiny that they're difficult to detect even with the best current instruments. A planet similar to Earth orbiting a Sun-like star at Earth's distance would cause a wobble of less than 1 meter per second, slower than walking pace. Detecting such minute velocity changes requires incredibly stable spectrographs and careful corrections for other sources of stellar variability, like star spots and convection in the star's atmosphere. The second major technique for finding exoplanets is the transit method, which has discovered more exoplanets than any other technique. A transit occurs when a planet passes directly in front of its star, as seen from Earth, blocking a tiny fraction of the star's light. For a Jupiter-sized planet transiting a Sun-like star, the star's brightness drops by about 1%. A small change, but definitely measurable with precise photometry. For an Earth-sized planet, the drop is much smaller, only about 0.01%, but still detectable with sufficiently sensitive instruments. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to detect transits. Kepler monitored the brightness of more than 150,000 stars continuously for over 4 years, searching for the telltale dips in brightness that indicates a planet passing in front of its star. The mission was spectacularly successful, discovering thousands of exoplanets and showing that planets are common. Most stars have at least one planet, and many have multiple planets. Transit observations provide information that radial velocity measurements cannot. The depth of the transit, how much the star's brightness decreases, reveals the planet's size. A bigger planet blocks more light, creating a deeper transit. The duration of the transit reveals information about the planet's orbital distance and the star's size. By combining transit observations with radial velocity measurements, astronomers can determine both the planet's size and its mass, which allows them to calculate its density and infer what it might be made of. A low-density planet is probably a gas giant like Jupiter. A high-density planet is likely rocky like Earth. A medium density might indicate a water world or a planet with a thick atmosphere. The transit method has limitations. It only works for planets whose orbits happen to be aligned edge-on from Earth's perspective. If a planetary system is tilted so that planets pass above or below the star rather than directly in front of it, no transits occur, and the planets remain undetectable by this method. Statistically, only a small fraction of planets are oriented correctly for transits to be visible from Earth. For a planet at Earth's distance from a Sun-like star, the probability of correct alignment is less than 1%. Despite this limitation, Kepler's strategy of monitoring thousands of stars simultaneously meant that even with low individual probabilities, many planets were discovered. Direct imaging represents the most straightforward approach, actually taking a picture of the planet next to its star, but it's also the most technically challenging. The problem is the enormous brightness difference. A Sun-like star is typically 10 billion times brighter than a Jupiter-like planet at visible wavelengths, and the planet sits right next to the star in the sky. Special techniques are required to block the star's light and reveal the faint planet. Coronagraphs, which create an artificial eclipse by placing a mask over the star, and star shades, which fly separately from the telescope and block the star's light before it enters the telescope, both enable direct imaging. Direct imaging works best for young, massive planets that are far from their stars. Young planets are still hot from their formation, glowing brightly in infrared light, making the contrast ratio more favorable. Planets farther from their stars are more separated in angle, making them easier to distinguish from the star's glare. Several dozen planets have been directly imaged, mostly young gas giants orbiting at large distances from their stars. These planets appear as faint dots of light in images taken with large, ground-based telescopes equipped with adaptive optics systems that correct for atmospheric blurring. Gravitational microlensing provides another method for detecting exoplanets, particularly useful for finding planets at large distances from Earth and planets far from their host stars. The technique relies on general relativity. When one star passes almost directly in front of a more distant background star from Earth's perspective, the foreground star's gravity acts as a lens, bending and focusing the background star's light. This creates a temporary brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence. Microlensing events are rare and unpredictable. You can't choose to observe a particular star and wait for a microlensing event. Instead, astronomers monitor millions of stars in dense stellar regions, like the galactic bulge, waiting for events to occur. When an event happens, it's unique. The same foreground and background star will never align again in human timescales. This makes follow-up observations challenging. but the method has discovered several dozen planets and is particularly good at finding planets in the outer reaches of planetary systems where other methods struggle. Astrometry measures the precise position of a star in the sky over time. If a planet is present, the star wobbles back and forth on the sky, shifting position slightly as both star and planet orbit their common center of mass. This is similar to the radial velocity method, but measures the wobble in position rather than in velocity. The wobble is extremely small. For Jupiter orbiting the Sun, as seen from a distance of 10 light-years, the wobble would be about half a millisecond, roughly equivalent to measuring the width of a human hair from a distance of 200 miles. The European Space Agency's Gaia mission, launched in 2013, is measuring the positions of over 1 billion stars with unprecedented precision, and it's beginning to detect the astrometric wobbles caused by giant planets. As Gaia continues its mission and accumulates more data, it will discover planets through astrometry and provide three-dimensional orbital information for many planets discovered by other methods. Each detection method has biases. It favors finding certain types of planets over others. Radial velocity finds massive planets close to their stars. Transits find planets of all masses, but only those aligned edge-on. Direct imaging finds young massive planets far from their stars. Microlensing finds planets at all distances but works best for planets far from their stars. By using multiple methods, astronomers build a more complete picture of the diversity of planetary systems. The combination of techniques has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury. Super-Earths, planets larger than Earth but smaller than Neptune, appear to be extremely common, yet don't exist in our solar system. Some systems have planets in extremely compact orbits, with multiple planets packed closer to their star than Mercury is to our Sun. Other systems have planets on highly eccentric orbits, stretching from close in to far out in elongated ellipses. Some planets orbit binary stars, experiencing sunsets with two suns like Luke Skywalker's home planet Tatooine in Star Wars. The atmospheres of exoplanets can be studied through transit spectroscopy. When a planet transits its star, some starlight filters through the planet's atmosphere on its way to Earth. Different molecules in the atmosphere absorb light at specific wavelengths, creating an absorption spectrum that reveals the atmospheric composition. Astronomers have detected water vapor, methane, carbon dioxide, and other molecules in exoplanet atmospheres. The James Webb Space Telescope, launched in 2021, is revolutionizing this field with its ability to detect even fainter spectral signatures and characterize the atmospheres of smaller, potentially habitable planets. The search for Earth-like planets in habitable zones, the region around a star where temperatures allow liquid water to exist on a planet's surface, drives much exoplanet research. Kepler discovered several candidates, including Kepler 452b, a planet slightly larger than Earth orbiting a Sun-like star at a distance where temperatures might support liquid water. Whether any of these planets actually harbour life remains unknown, but the discovery that Earth-sized planets in habitable zones exist at all is profound. We're no longer wondering whether such planets exist, but rather whether any of them host life. Future missions will improve our ability to find and characterize Earth-like planets. The Nancy Grace Roman Space Telescope will use microlensing and direct imaging to find planets. Ground-based extremely large telescopes currently under construction will directly image planets and study their atmospheres in detail. Proposed missions like the Habitable Worlds Observatory aim to directly image dozens of Earth-like planets and search their atmospheres for biosignatures, gases like oxygen and methane that might indicate the presence of life. In less than 3 decades, exoplanet science has progressed from the first tentative discovery to finding thousands of planets, characterizing their properties, studying their atmospheres, and identifying candidates that might harbour life. The methods astronomers developed to overcome the challenge of finding tiny, faint planets next to brilliant stars have succeeded beyond initial expectations, revealing that planets are not rare accidents but common outcomes of star formation. That our solar system is just one example among billions of planetary systems filling the galaxy, and that the question of whether we're alone in the universe might finally be answerable through observations of the atmospheres of distant worlds orbiting alien suns. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light. And energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has two protons and one neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, two helium-3 nuclei collide and fuse, forming ordinary helium-4, which has two protons and two neutrons, and releasing two protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into one helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity, Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the sun is actually a fairly average, middle-sized star. Some massive stars output 1,000,000 times more energy than the sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. How life could survive on rogue planets. Most planets orbit stars, bathed in starlight that provides warmth and energy for any life that might evolve. But scattered throughout the galaxy are worlds that wander alone through the darkness of interstellar space. Rogue planets, ejected from their birth solar systems through gravitational interactions, or perhaps forming in isolation, drifting for billions of years without a sun to orbit. These orphaned worlds seem like the least hospitable places imaginable for life. Cut off from starlight, they receive no external heat source, no energy for photosynthesis, no warming to maintain liquid water on their surfaces. Yet despite these apparently insurmountable obstacles, life might still find ways to survive on rogue planets, drawing on internal heat sources, subsurface environments, and the remarkable adaptability that evolution has demonstrated countless times on Earth when organisms colonize seemingly impossible habitats. The key to habitability on rogue planets is internal heat. Unlike stars, which generate heat through nuclear fusion, rogue planets must rely on residual heat from formation and ongoing heat from radioactive decay of elements in their interiors. When planets form, the process of accretion, countless collisions between smaller bodies that gradually build up the planet, converts kinetic energy into heat. Additionally, gravitational compression, as material piles up, releases energy that heats the planet's interior. A newly formed planet is molten or partially molten taking millions to billions of years to cool. This primordial heat, combined with heat from radioactive decay of uranium, thorium, potassium, and other radioactive isotopes in the planet's rocks, keeps planetary interiors warm for billions of years. Earth itself generates about 47 terawatts of internal heat, roughly equal to 10,000 large power plants operating continuously. Most of this heat comes from radioactive decay, with some contribution from residual primordial heat and from crystallization of Earth's molten iron core. This internal heat drives plate tectonics, powers volcanic activity, and maintains Earth's magnetic field. A rogue planet of similar size and composition would generate similar amounts of internal heat, regardless of whether it orbits a star or drifts through interstellar space. The challenge is keeping that heat trapped. Without an atmosphere, heat would radiate directly into space, and the planet's surface would quickly reach temperatures only a few degrees above absolute zero. The background temperature of the universe, about -270 degrees Celsius. But a substantial atmosphere could act as insulation, trapping heat through the greenhouse effect and maintaining warmer temperatures at the surface or in the lower atmosphere, even without any external heat source. A rogue planet with a thick hydrogen atmosphere could potentially maintain surface temperatures warm enough for liquid water through atmospheric pressure and greenhouse warming alone. Hydrogen is the lightest and most abundant element in the universe, and large planets can capture and retain massive hydrogen envelopes during formation. The greenhouse effect from a thick hydrogen atmosphere, combined with internal heat radiating from below, could create a temperature profile that allows liquid water to exist at the surface or at some depth within the atmosphere, where pressure and temperature are both suitable. Computer models suggest that a rogue planet several times Earth's mass, with a hydrogen atmosphere perhaps 100 times more massive than Earth's atmosphere, could maintain surface temperatures above the freezing point of water for billions of years, powered only by internal heat. Such a planet would be entirely dark at the surface, no day or night, just eternal darkness. But it would be warm enough for liquid water, and where there's liquid water and a source of energy, life becomes possible. Life on such a world could not depend on photosynthesis, but that's not necessarily a problem. On Earth, entire ecosystems exist in permanent darkness, sustained by chemosynthetic bacteria that extract energy from chemical reactions rather than sunlight. Deep-sea hydrothermal vents host thriving communities where bacteria oxidize hydrogen, sulfide, methane, or hydrogen, using the chemical energy to build organic molecules from carbon dioxide. These chemosynthetic bacteria form the base of food chains that support tube worms, clams, fish, and crustaceans, all living in absolute darkness, kilometers beneath the ocean surface. A rogue planet with liquid water oceans, maintained by internal heat and atmospheric greenhouse warming, could develop similar chemosynthetic ecosystems. Volcanic activity would vent gases like hydrogen, hydrogen sulfide, methane, and carbon dioxide into the water and atmosphere. Bacteria could evolve to extract energy from these chemicals, building organic molecules that could support more complex organisms. The entire biosphere would operate on chemical energy from the planet's interior rather than solar energy, making the planet's life forms independent of any star. Subsurface oceans represent an even more plausible habitat for life on rogue planets. Many worlds in our solar system likely have liquid water oceans beneath ice shells. Europa, Enceladus, possibly Titan, Ganymede, Callisto, Pluto, and other bodies. These oceans are kept liquid by tidal heating from their parent planets, or by internal radioactive heating. A rogue planet with sufficient internal heat and a thick ice shell could maintain a subsurface ocean indefinitely, with the ice providing insulation that prevents the ocean from freezing while protecting it from the harsh radiation and extreme cold of interstellar space. The ice shell on a rogue planet might be very thick, perhaps tens or hundreds of kilometers, creating an insulating layer that traps internal heat far more effectively than any atmosphere. The ocean beneath this ice would be completely dark, protected from the radiation that fills interstellar space, and stable for billions of years. Temperature would be maintained by heat flowing from the rocky mantle below. Hydrothermal vents on the ocean floor would provide chemicals and energy for chemosynthetic life. Such an ocean might be an ideal habitat, more stable than surface oceans on planets orbiting stars where stellar evolution, asteroid impacts, and climate variations create periodic catastrophes. Life in a subsurface ocean on a rogue planet would never know stars exist. The entire biosphere would be confined to the dark ocean, with the ice ceiling above and rocky floor below defining the limits of the habitable universe. Evolution would never produce eyes sensitive to visible light, because no visible light exists. Organisms might instead evolve chemical sensing, pressure sensing, electroreception, or other non-visual senses. Intelligence, if it evolved, would develop without ever seeing stars, planets, or anything beyond the ocean's boundaries. Such a civilization might not even realize that a larger universe exists beyond their world, having no way to detect or observe the space around them through kilometers of ice. Geothermal pockets could create localized habitable zones even on rogue planets without global oceans. Volcanic activity or concentrations of radioactive elements could heat specific regions. Melting ice to create underground lakes or pockets of liquid water embedded in ice. These isolated water bodies might be small, perhaps only a few kilometers across, but they could persist for millions of years, long enough for life to evolve and diversify within each pocket. Different pockets might develop different ecosystems in isolation from each other, creating multiple independent evolutionary experiments on a single rogue world. Atmosphere composition would profoundly affect habitability. A rogue planet that retained or captured a hydrogen-helium atmosphere during formation could use that atmosphere's greenhouse effect to maintain warmth. Carbon dioxide, methane, and ammonia are all more effective greenhouse gases than hydrogen and would enhance warming at much lower atmospheric masses. A rogue planet with a thick carbon dioxide atmosphere and substantial internal heat might maintain temperatures warm enough for liquid water with a much thinner atmosphere than a hydrogen-dominated world would need. The size of the rogue planet matters significantly. Larger planets generate more internal heat from radioactive decay simply because they contain more radioactive material. Larger planets can also hold thicker atmospheres through stronger gravity and lose heat more slowly because their surface area to volume ratio is smaller. Heat escapes through the surface, but heat is generated throughout the volume, so larger planets stay warm longer. A rogue super-Earth several times, Earth's mass might remain habitable for far longer than an Earth-mass rogue planet, potentially maintaining surface or subsurface liquid water for tens of billions of years or more. Very small rogue planets, Mars-sized or smaller, would struggle to maintain habitability. They would cool quickly, losing internal heat within a few billion years. Their weak gravity would allow atmospheric escape, making it difficult to maintain the thick atmospheres needed for greenhouse warming. However, even small rogue worlds might maintain subsurface liquid water in deep aquifers or isolated pockets warmed by concentrations of radioactive elements or by residual heat from formation for some period after being ejected from their parent system. The abundance of rogue planets remains uncertain, but some estimates suggest they might outnumber stars. If planets are commonly ejected during the chaotic early phases of planetary system formation, the galaxy might contain billions or even trillions of rogue planets drifting through interstellar space. Most would be cold, dark, and apparently lifeless at their surfaces, but some fraction might maintain subsurface oceans or possess the right combination of size, composition, and atmosphere to support life in hidden biospheres beneath ice or in dark surface oceans sustained by nothing more than the planet's internal warmth. Detecting life on rogue planets would be extraordinarily challenging. These worlds emit no reflected starlight, making them nearly impossible to detect through traditional astronomical methods. They can only be detected through gravitational microlensing. When a rogue planet passes in front of a distant star from Earth's perspective, its gravity briefly magnifies the star's light, or through direct detection of their infrared emission, the faint heat radiating from their surfaces. Neither method provides information about atmospheres, surface conditions, or potential habitability, let alone biosignatures. Future infrared telescopes might be able to detect the warmest rogue planets and potentially characterize their atmospheres if those atmospheres are thick enough to produce detectable spectral features. Finding methane, carbon dioxide, or other gases in unexpected ratios might hint at biological activity, though distinguishing biological from geological sources would be nearly impossible without additional information. Direct exploration by spacecraft seems impractical, given the vast distances between stars and the difficulty of even locating rogue planets, let alone traveling to them. The evolutionary trajectory of life on rogue planets might differ fundamentally from life on planets orbiting stars. Without the regular day-night cycle that drives circadian rhythms on Earth, organisms would have no reason to evolve time-keeping mechanisms tied to planetary rotation. Without seasons caused by axial tilt and orbital motion, there would be no seasonal cycles, no annual rhythms. Life would exist in an eternal, unchanging environment, at least on timescales shorter than geological epochs, potentially leading to very different evolutionary pressures than life on Earth experiences. The isolation of rogue planets creates another interesting possibility. These worlds might serve as interstellar arcs, carrying life between star systems. If a planet with a biosphere is ejected from its home system, life on that planet doesn't necessarily die. If the planet maintains subsurface oceans, through internal heating, life in those oceans could survive indefinitely, potentially for billions of years, as the planet drifts through the galaxy. Eventually, such a planet might be captured by another star system, or it might pass close to a star that warms the planet temporarily, allowing surface life to revive if it was dormant. This mechanism, planets carrying life between star systems, represents a form of panspermia that could spread life throughout the galaxy. How life could survive on rogue planets demonstrates the resilience and adaptability of biology when provided with even minimal requirements. Liquid water, chemical energy, raw materials, and time. A rogue planet, cut off from all starlight, drifting through the darkness of interstellar space for billions of years, seems like an impossible place for life. Yet internal heat and thick atmospheres, or ice shells, could create hidden habitats where chemosynthetic ecosystems thrive in eternal darkness, where evolution operates unconstrained by day-night or seasonal cycles, where intelligent beings might arise never knowing that stars exist, and where life demonstrates its ultimate independence from sunlight, proving that biology requires not a sun to orbit, but merely the right chemical conditions and energy sources, expanding the definition of habitable environments to include not just planets in stellar habitable zones, but potentially countless dark worlds adrift in the spaces between the stars, each one a potential harbour for life in the vast ocean of the galaxy. How planets form from dust. In the beginning, there were no planets, no Earth, no Jupiter, no rocky worlds or gas giants, just vast clouds of gas and dust drifting through the galaxy. Yet from these diffuse, seemingly formless clouds, gravity and physics conspired to build the solid worlds we see today. Understanding how planets form from dust means understanding one of nature's most remarkable construction projects, a process that transforms microscopic particles floating in space into spheres thousands of miles across. complete with cores, mantles, atmospheres, and sometimes even moons. The story begins with a molecular cloud, a cold, dark region of space, filled primarily with hydrogen and helium gas left over from the Big Bang, mixed with about 1% heavier elements and dust particles created in previous generations of stars. These dust grains are tiny, typically only a fraction of a micrometer across, smaller than bacteria. They're composed of silicates, rocky minerals similar to sand, and sometimes ices of water, carbon dioxide, or methane, depending on the temperature of the cloud. Something disturbs the cloud. Perhaps a nearby star explodes as a supernova, sending a shockwave rippling through space. Perhaps the cloud passes through a spiral arm of the galaxy where gas is compressed. Whatever the trigger, a region of the cloud begins to collapse under its own gravity. As it collapses, it spins faster due to conservation of angular momentum. The same principle that makes a figure skater spin faster when pulling their arms inward. The collapsing cloud flattens into a disk, a swirling pancake of gas and dust with a growing concentration of mass at the center. This is a protoplanetary disk, and it's where planets will form. The center grows hotter and denser as material falls inward, eventually becoming a protostar that will ignite nuclear fusion and become a star. But the disk surrounding the star contains enough material to build an entire family of planets. In the disk, dust particles drift through the gas, occasionally bumping into each other. When they collide gently, they can stick together. The sticking happens through several mechanisms. Sometimes electrostatic forces, essentially static electricity, cause particles to cling to each other. Sometimes molecular forces, similar to the forces that make wet sand stick together, bind the particles. Ice coatings on particles in the colder outer regions of the disk act like glue, making particles particularly sticky. These gentle collisions build larger particles. A dust grain collides with another, and they stick, forming a slightly larger grain. This larger grain has a bigger cross-section, making it more likely to encounter and stick to other grains. Slowly, grain by grain, the particles grow from microscopic dust into pebbles, then into rocks, then into boulders. This process, called accretion, is slow at first but accelerates as particles grow larger. The growing clumps begin to settle toward the midplane of the disk, the thin central plane where the density is highest. Larger particles settle faster than smaller ones because they're less buffeted by gas turbulence. The midplane becomes a dense layer of solid material embedded in the gas disk, creating favorable conditions for further growth. Particles collide more frequently in this dense environment, accelerating the growth process. When the solid objects reach sizes of about a kilometer across, they're called planetesimals. These are the building blocks of planets, and reaching this size represents a critical milestone. Objects this large have enough gravity to begin attracting nearby material rather than relying solely on chance collisions. Their gravity pulls in smaller rocks and dust, causing them to grow faster. The biggest planetesimals grow the fastest because their stronger gravity allows them to clear out larger regions of the disk, creating what astronomers call runaway growth. The protoplanetary disk is a chaotic place. Planetesimals don't just grow peacefully, they also collide with each other. Some collisions are gentle enough that the objects merge, creating larger bodies. But other collisions are violent, shattering one or both objects into fragments. Whether a collision leads to growth or destruction depends on the relative velocities. Slow collisions, at a few meters per second, tend to result in sticking and growth. Fast collisions at kilometers per second tend to be destructive. Over time, certain planetesimals become dominant, growing larger than their neighbors. These become planetary embryos, objects roughly the size of our Moon or Mars, hundreds to thousands of kilometers across. The largest embryos in each region of the disk sweep up most of the available material in their vicinity, clearing out their orbital zones. When two similarly sized embryos eventually collide, the impact can be cataclysmic, melting both objects and creating a larger planet from the merged material. The composition of forming planets depends on their distance from the star. Close to the star, temperatures are high, hot enough that volatile materials like water, methane, and ammonia can't condense into solid form. Only materials with high melting points, metals and rocky minerals, can exist as solids. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are rocky worlds made of iron and silicates. Farther from the star, beyond a boundary called the snow line or ice line, temperatures are cold enough for water to freeze into ice. This fundamentally changes planet formation. Because ice is abundant, there's simply more solid material available when you include ice along with rock and metal. The snow line in our solar system was located somewhere around where the asteroid belt is today, between Mars and Jupiter. Beyond the snow line, planetary embryos could grow much larger because more solid material was available. When an embryo grew to roughly 10 times Earth's mass, something dramatic happened. Its gravity became strong enough to capture gas directly from the surrounding disk. Hydrogen and helium, the most abundant elements in the disk, began falling onto the growing planet. Once this process started, it ran away rapidly. The planet's gravity pulled in more gas, which made it more massive, which increased its gravity, which allowed it to pull in even more gas. This runaway gas accretion created the gas giant planets, Jupiter and Saturn, in our solar system. These worlds are mostly hydrogen and helium, like miniature stars, with relatively small rocky and icy cores buried beneath thousands of kilometers of gas. Jupiter grew so large and so quickly that it dominated its region of the solar system, its powerful gravity stirring up the asteroid belt and preventing the material there from ever forming a planet. Uranus and Neptune, the ice giants, also formed beyond the snow line, but grew more slowly. They captured some gas from the disk, but not as much as Jupiter and Saturn, possibly because the gas in their region was less dense or because the disk dispersed before they could grow large enough to undergo runaway gas accretion. These planets are dominated by water, methane, and ammonia ices, rather than hydrogen and helium gas. The protoplanetary disk doesn't last forever. The young star at the center begins generating powerful stellar winds and intense radiation. Over a few million years, this wind sweeps away the remaining gas in the disk, ending the era of planet formation from gas accretion. Any planets that hadn't finished growing could no longer capture gas from the disk. This probably explains why Mars is so small. It formed in a region where less material was available, and the gas dispersed before it could grow much larger. Even after the gas disk disperses, planet formation continues through collisions between the remaining planetesimals and planetary embryos. This era, called the late heavy bombardment or giant impact phase, was violent. Computer simulations suggest that the inner solar system initially formed several more planetary embryos than the 4 terrestrial planets we see today. These embryos had chaotic, crossing orbits, and they repeatedly collided over tens of millions of years. Eventually, through this sequence of giant impacts, the embryos merged into the 4 stable planets, Mercury, Venus, Earth, and Mars, we observe today. Earth's moon likely formed during one of these giant impacts. About 4.5 billion years ago, a Mars-sized object struck the young Earth at an oblique angle. The impact vaporized both the impactor's outer layers and a large portion of Earth's mantle, ejecting an enormous amount of material into orbit around Earth. This material, a mixture of vaporized rock and molten droplets, quickly coalesced into the Moon. The Moon's composition, which closely matches Earth's mantle but lacks iron from Earth's core, supports this giant impact origin. The timing of planet formation varies. In our solar system, Jupiter formed within a few million years, fast enough to capture gas before the disk dispersed. The terrestrial planets took longer, perhaps tens of millions of years to reach their final sizes. The final giant impacts on Earth, including the moon-forming impact, occurred somewhere around 50 to 100 million years after the disk first started collapsing. This might seem long, but it's less than 1% of Earth's current age. Planet formation is remarkably quick on astronomical timescales. Not all the material in the protoplanetary disk becomes part of planets. Some planetesimals survive in stable regions where planets didn't form. The asteroid belt contains remnants of planetesimals that never accreted into a planet, stirred up and prevented from merging by Jupiter's gravitational influence. The Kuiper belt beyond Neptune and the more distant Oort cloud contain frozen planetesimals preserved from the solar system's formation, rich in ices that couldn't exist in the warmer inner regions. Observations of protoplanetary disks around young stars show this process happening in real time. The Atacama Large Millimeter Array in Chile has captured stunning images of disks with gaps and rings, structures created by forming planets as they clear out their orbital zones. Some disks show spiral patterns caused by gravitational perturbations from massive planets still embedded in the disk. These observations confirm that planet formation is common and that the process we see in our solar system occurs around most stars. Planet formation doesn't always produce systems like ours. Exoplanet discoveries have revealed hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. These planets must have formed farther out beyond the snow line, where ice could exist, then migrated inward through gravitational interactions with the disk or with other planets. Some planetary systems are extremely compact, with multiple planets orbiting closer to their star than Mercury. Others have planets on highly elliptical orbits, unlike the nearly circular orbits in our solar system. From microscopic dust grains to planet-sized worlds represents a journey across more than 10 orders of magnitude in size, a factor of tens of billions. The process transforms diffuse material spread across millions of miles into concentrated spheres where gravity compresses matter so intensely that planetary interiors melt and differentiate into layers, where atmospheres form and weather patterns emerge, and where, at least on one planet we know of, conditions become suitable for life to arise. All of this complexity, all of this structure, emerges from nothing more than dust, gas, gravity, and time, following the laws of physics that govern how matter behaves when concentrated by the inexorable pull of gravity in the rotating disk around a young star. How planets get their beautiful rings. When you think of planetary rings, Saturn immediately comes to mind, with its magnificent system of bright bands encircling the planet like a cosmic halo. But Saturn isn't alone in possessing rings. Jupiter, Uranus, and Neptune all have ring systems of their own, though far less prominent. Even some asteroids have been discovered with tiny rings circling them. These structures, some broad and bright, others narrow and faint, all share a common origin story rooted in gravity, orbital mechanics, and the sometimes violent history of the solar system. The basic ingredients for planetary rings are surprisingly simple. Countless small particles, ranging from dust grains smaller than smoke particles to chunks of rock and ice the size of houses, all orbiting a planet in a flat disk. What makes rings special isn't the individual particles but their collective behaviour, the way millions or billions of objects interact through gravity and collisions to create structures that can span hundreds of thousands of miles yet be only tens of meters thick. Rings form through several different mechanisms, and understanding these processes means understanding both creation and destruction, both gentle accumulation and catastrophic violence. The first and perhaps most dramatic way rings can form is through tidal disruption. Every planet generates a gravitational field that weakens with distance, and this creates tidal forces on any object orbiting nearby. If you imagine a moon orbiting close to a planet, the side of the moon facing the planet experiences stronger gravity than the side facing away. This difference in gravitational pull creates a stretching force that tries to pull the Moon apart. There's a critical distance from any planet, called the Roche limit, inside which these tidal forces become stronger than the Moon's own gravity holding it together. Cross this threshold, and the Moon cannot remain intact. If a moon migrates inward through various processes, or if it formed inside this limit, it will be torn apart by tidal forces. The material doesn't disappear, it spreads out along the Moon's orbital path, and over time, through collisions and gravitational interactions, it forms a flat ring around the planet. Picture this process in your mind. A small moon, perhaps captured from elsewhere in the solar system or formed in orbit around the planet, slowly spirals inward. Tidal interactions with the planet transfer energy and angular momentum, gradually changing the Moon's orbit. As it crosses the Roche limit, cracks begin to form. Pieces break away, first small fragments, then larger chunks. The Moon doesn't explode dramatically, it comes apart more gradually, like pulling apart a piece of bread. Each fragment continues orbiting the planet independently, and as they collide and break into smaller pieces, they spread into a disk of debris. This process may have created some of Saturn's rings, though the origin of Saturn's ring system remains one of the great puzzles in planetary science. The rings are remarkably bright and rich in water ice, suggesting they might be relatively young, perhaps only a few 100 million years old, rather than as ancient as the solar system itself. One theory suggests that a small icy moon, perhaps 200 miles across, wandered too close to Saturn and was torn apart by tidal forces. The shattered remains spread into the magnificent ring system we see today. Another way rings form is through collisions. Imagine two moons orbiting a planet on paths that eventually intersect, or an asteroid from elsewhere in the solar system crashing into a moon. The impact releases tremendous energy, shattering both objects and ejecting debris into space. Some of this material falls back onto the planet or escapes entirely, but much of it remains in orbit, gradually spreading into a ring. This collision scenario might explain some of the fainter, darker ring systems. Jupiter's rings, for instance, are composed of very small dust particles that appear reddish-brown, suggesting they might come from meteorite impacts onto small inner moons. When a meteorite strikes one of these tiny moons, it kicks up dust that then orbits Jupiter. This dust doesn't stay in the ring system forever. It gradually spirals inward due to interactions with Jupiter's magnetic field and atmospheric drag, but it's constantly replenished by new impacts. Rings can also form from a volcanic activity on moons, though this is a less common mechanism. Jupiter's moon, Io, is the most volcanically active body in the solar system, with eruptions constantly spewing material into space. Some of this material, particularly atoms of sodium and sulfur, forms extended clouds around Jupiter. While not a traditional ring of solid particles, these atomic clouds occupy ring-like regions and show that rings can have diverse origins and compositions. The shepherd moon mechanism plays a crucial role in maintaining and shaping rings once they form. Small moons orbiting just inside or outside a ring can gravitationally interact with ring particles, confining them to narrow bands. Imagine a ring particle in an orbit that would normally cause it to drift outward. As it approaches a shepherd moon, orbiting outside the ring, the moon's gravity tugs on it, altering its orbit and deflecting it back toward the ring. Similarly, a shepherd moon orbiting inside the ring can prevent particles from drifting inward. These gravitational interactions can create remarkably sharp ring edges and can even maintain gaps within ring systems. Saturn's moon Prometheus and Pandora act as shepherd moons for the narrow F ring, one of Saturn's outermost rings. The F ring is only a few hundred miles wide, but thousands of miles long, and without these shepherd moons, it would spread out and dissipate over time. The moon's gravity creates a delicate balance, continuously sculpting the ring into its narrow form. Resonances add another layer of complexity to ring formation and structure. When ring particles orbit at certain specific distances from a planet, their orbital period can be a simple fraction of a moon's orbital period, perhaps half as long, or a third or 2/5. At these resonant locations, the gravitational tugs from the moon occur at the same point in each orbit, adding up over time and creating powerful effects. Resonances can clear gaps in rings, sweeping particles out of certain orbital paths, or they can concentrate particles, creating narrow ringlets. The Cassini division, the prominent gap in Saturn's rings, visible even through small telescopes from Earth, exists primarily because of a resonance with the moon Mimas. Particles orbiting in the Cassini division have an orbital period exactly half that of Mimas. The repeated gravitational interactions at this resonance gradually push particles into different orbits, maintaining a gap nearly 3,000 miles wide. The particles within rings are not static, they're constantly colliding with each other, and these collisions shape the ring's structure and evolution. When two chunks of ice collide gently in Saturn's rings, they might stick together, growing larger. But more energetic collisions shatter particles into smaller pieces. There's a balance between these processes, and over time, rings develop a characteristic size distribution of particles, with many small particles and fewer large ones. These collisions also dissipate energy, causing the ring to flatten. Imagine particles orbiting at slightly different inclinations, some tilted a bit relative to others. When they collide, the vertical component of their motion is randomized and gradually damped out through repeated collisions. The result is that rings become extraordinarily thin relative to their width. Saturn's main rings span about 175,000 miles from inner edge to outer edge, yet they're typically only about 30 feet thick, a ratio that's thinner than a sheet of paper if scaled down. Temperature plays a role in ring dynamics as well. Ring particles are heated by sunlight and cooled by radiating infrared energy into space. The equilibrium temperature depends on the particle's size and composition. Larger particles have more thermal inertia and cool more slowly, while smaller particles respond quickly to changes in sunlight. These temperature variations affect how particles stick together when they collide, influencing whether the ring evolves toward larger clumps or maintains a population of smaller particles. The composition of ring particles varies widely between different planets and even within a single ring system. Saturn's rings are predominantly water ice, giving them their high reflectivity and bright appearance. The ice is remarkably pure, though there are trace amounts of rocky material and organic compounds that give some regions a slightly reddish or brownish tint. Uranus's rings, by contrast, are much darker, composed of material that reflects only a few % of the light that hits it. This dark material might be radiation-processed organic compounds, similar to the dark material found on some asteroids and comets. The age of ring systems is a matter of ongoing research and debate. Some rings might be primordial, dating back to the formation of the solar system itself 4.6 billion years ago. These would be rings made from material that was present in the disk of gas and dust from which the planets formed. Material that never coalesced into moons because it was inside the Roche limit. Other rings are clearly much younger, formed by relatively recent collisions or tidal disruptions. Saturn's rings, despite their prominence, might be surprisingly young. Several lines of evidence suggest they could be only a few 100 million years old. They're very bright and icy, lacking the darkening that would come from billions of years of meteorite bombardment. The amount of dust falling into Saturn's atmosphere from the rings suggests they're being depleted at a rate that couldn't be sustained over billions of years. If Saturn's rings are indeed young, it means we're living at a special time in the solar system's history, able to witness these magnificent structures during a brief window of their existence. Rings are not permanent features. They evolve over time, gradually spreading outward or inward, losing material to the planet's atmosphere or to moons, being disrupted by resonances or replenished by new collisions. Some ring systems might last for the lifetime of the solar system, while others might come and go over much shorter timescales. The rings we see today are snapshots in an ongoing process of creation, evolution, and eventual destruction. Even Earth might have had rings at some point in its distant past. Some researchers have suggested that a large impact that created debris in orbit could have temporarily given Earth a ring system that persisted for millions of years before the material either fell back to Earth or coalesced to form the Moon. While speculative, this idea reminds us that ring systems are dynamic features that can appear and disappear throughout a planet's history. The physics governing ring formation operates not just in our solar system, but around planets orbiting other stars as well. Exoplanets with large moon systems or recent collisions might sport ring systems, though detecting such rings at interstellar distances remains incredibly challenging with current technology. The same fundamental processes, tidal disruption, collisions, gravitational interactions, would operate universally, creating rings around any planet where conditions permit, adding layers of complexity and beauty to planetary systems throughout the galaxy. How the Moon pulls on Earth's oceans. Twice each day, the ocean rises up beaches and coastlines around the world, then retreats back toward the sea. This rhythmic rise and fall of the tides has shaped human civilization for thousands of years, governing when ships could enter harbours, when fishermen could gather shellfish from tidal pools, and when coastal communities needed to prepare for high water. The connection between these tides and the Moon was recognised in ancient times, but understanding exactly how the Moon creates tides requires thinking carefully about gravity, how it varies with distance, and how Earth's ocean responds to forces that stretch and squeeze it in complex ways. The fundamental cause of tides is gravity, but not gravity in the simple sense of the Moon pulling water toward itself. If that were the entire story, we would see one bulge of water on the side of Earth facing the Moon, and that would be the end of it. Instead, we observe two tidal bulges, one on the side facing the Moon and another on the opposite side of Earth. This puzzling fact confused natural philosophers for centuries, until Isaac Newton, in his Principia Mathematica, published in 1687, provided the correct explanation using his law of universal gravitation and his laws of motion. The key insight is that the Moon's gravity pulls on every part of Earth, but it pulls with different strengths depending on distance. The side of Earth closest to the Moon experiences stronger gravitational attraction than Earth's centre, which in turn experiences stronger attraction than the far side. This difference in gravitational force across Earth's diameter creates what are called tidal forces, forces that try to stretch Earth along the line, connecting it to the Moon, while simultaneously squeezing it perpendicular to that line. Imagine Earth's structure for a moment. The solid rock of Earth's crust and mantle resists deformation quite strongly. While tidal forces do deform the solid Earth slightly, raising and lowering the ground by about a foot, the effect is not dramatic because rock is stiff and strong. The oceans, however, are fluid. They can flow freely in response to forces, and they respond readily to the tidal forces that the solid Earth largely resists. Consider a point on Earth's surface directly beneath the Moon. The water at this location is about 4,000 miles closer to the Moon than Earth's centre. The Moon's gravitational pull weakens with distance according to an inverse square law. Double the distance and the force becomes 1/4 as strong. This means the ocean on the near side experiences a gravitational pull toward the Moon that's about 7% stronger than the pull experienced by Earth's centre. This differential force pulls the ocean away from Earth's centre, creating a bulge of water on the moon-facing side. Now consider the opposite side of Earth, the point farthest from the moon. Here the ocean is about 4,000 miles farther from the moon than Earth's center. The gravitational pull from the moon at this location is about 7% weaker than at Earth's center. Earth's center is being pulled toward the moon more strongly than the water on the far side, effectively pulling Earth away from the water and leaving the water behind. The result is another bulge on the side opposite the moon. This creates the characteristic two-bulge pattern. If you could freeze time and look at Earth from space, you would see the oceans slightly elongated along the Earth-Moon line, with high water on both the near and far sides and low water at the points 90 degrees away from the moon. As Earth rotates beneath these bulges, any given point on Earth's surface passes through two high tides and two low tides each day, though not exactly every 12 hours, because the moon is also moving in its orbit, shifting the position of the bulges over time. The height of these tidal bulges would be quite modest if they responded only to the moon's gravitational pull, perhaps a foot or two in the open ocean. But the actual tides we observe at coastlines can be dozens of feet high. This amplification occurs because of the way ocean basins are shaped and because of resonance effects as water sloshes back and forth in confined spaces. The Bay of Fundy in Canada experiences the world's highest tides, sometimes exceeding 50 feet, because the bay's shape and size create a natural resonance that amplifies the tidal forcing from the moon and sun. The sun also creates tides on Earth, though they're smaller than lunar tides despite the sun's vastly greater mass. The reason is distance. The sun is about 400 times farther from Earth than the moon, and tidal forces depend not just on mass but on how much the gravitational pull varies across Earth's diameter. The sun's great distance means its gravitational pull varies less across Earth than the moon's does, making solar tides about 46% as strong as lunar tides, a ratio that Pierre-Simon Laplace calculated in detail in his comprehensive work on celestial mechanics in the late 1700s. The interaction between solar and lunar tides creates the familiar spring and neap tide cycle. When the moon and sun align, either on the same side of Earth during a new moon or on opposite sides during a full moon, their tidal effects add together, creating spring tides with especially high tides and especially low tides. The name has nothing to do with the season, but comes from the idea that the tides spring forth. When the moon and sun are at right angles as seen from Earth during first and third quarter moons, their tidal effects partially cancel, creating neap tides with smaller tidal ranges. This 2-week cycle of spring and neap tides is predictable and was well understood by ancient mariners, though they lacked Newton's gravitational explanation for why it occurred. The timing of tides is not as simple as one might expect. If you observe the tides at any coastal location, you'll notice that high tide doesn't occur exactly when the moon is overhead or exactly when it's on the opposite side of Earth. There's typically a delay of several hours called the tidal lag. This occurs because the ocean cannot respond instantaneously to the changing tidal forces. Water has inertia, it takes time to accelerate and decelerate, and friction between the moving water and the ocean floor dissipates energy, creating phase lags between the tidal forces and the ocean's response. These friction effects have profound long-term consequences. As tidal bulges try to follow the moon, but are dragged forward slightly by Earth's rotation, they create a gravitational pull on the moon that's not perfectly aligned with the Earth-Moon line. This misaligned pull acts to accelerate the moon in its orbit, gradually increasing its orbital energy and causing it to move away from Earth. Precise laser ranging measurements using reflectors left on the moon by Apollo astronauts have confirmed that the moon is receding from Earth at about 1.5 inches per year. This recession cannot continue indefinitely at the current rate. As the moon moves farther away, tidal effects weaken, slowing the recession. But over the 4.5 billion years since the moon formed, likely from debris created when a Mars-sized object collided with the young Earth. The moon has moved substantially farther from Earth. Early in Earth's history, when the moon was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles, tidal forces were enormously stronger. Tides might have been hundreds of feet high, and the moon would have appeared many times larger in the sky, looming over the horizon like an enormous sphere dominating the heavens. The energy dissipated by tidal friction doesn't just affect the moon's orbit, it also affects Earth's rotation. The gravitational drag from the tidal bulges acts to slow Earth's rotation gradually. Each century, Earth's day lengthens by about 1.7 milliseconds. This seems negligible, but over geological time, it accumulates. Fossil evidence from ancient corals, which show daily growth bands much like tree rings, indicates that 400 million years ago, Earth's day was only about 22 hours long, and a year contained about 400 days. The moon was closer, Earth rotated faster, and tides were stronger. This tidal interaction between Earth and the moon is an example of tidal locking in progress. The moon is already tidally locked to Earth, always showing the same face toward Earth because tidal forces from Earth have synchronized the moon's rotation period with its orbital period. Earth is gradually becoming tidally locked to the moon as well, though this process will take tens of billions of years to complete, longer than the remaining lifetime of the Sun. If it could be completed eventually, Earth would always show the same face to the moon, and the moon would hang stationary in the sky over one hemisphere, never visible from the other. Other bodies in the solar system experience even more extreme tidal effects. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated internally by tidal flexing. As Io orbits Jupiter in an elliptical path, the tidal forces it experiences vary in strength, squeezing and stretching the moon's interior. This constant kneading generates tremendous heat through friction, keeping Io's interior molten and driving its spectacular volcanic eruptions. This process, predicted by Stanton Peele and colleagues just before the Voyager spacecraft discovered Io's volcanism in 1979, is called tidal heating. Saturn's moon Enceladus experiences similar tidal heating, though less extreme than Io. The heat from tidal flexing keeps a subsurface ocean liquid beneath Enceladus's icy crust, and tidal stresses crack the ice at the South Pole, allowing geysers of water to erupt into space. Europa, another moon of Jupiter, likely has its subsurface ocean maintained by tidal heating as well, making it one of the most promising places to search for life beyond Earth. Tidal forces can also be destructive. Every large body creates a tidal limit, called the Roche limit, after Edouard Roche, who calculated it in 1848, inside which tidal forces exceed the self-gravity holding a satellite together. A moon that wanders inside the Roche limit will be torn apart by tidal forces, pulled into fragments that spread into a ring around the planet. Saturn's magnificent ring system may have originated this way, from a moon that either formed inside the Roche limit or migrated inward and was disrupted. Tidal forces operate throughout the universe. Binary stars experience tides that can transfer mass from one star to its companion. Black holes create tidal forces so extreme that they can tear apart stars that pass too close, creating spectacular tidal disruption events. Galaxies passing near each other experience tidal forces that stretch them into long streams of stars, creating the tidal tails visible in many interacting galaxies. The same physics that causes ocean tides on Earth, the differential pull of gravity across an extended object, operates on scales from moons and planets to stars and galaxies. The tides we observe at the beach are the local manifestation of a cosmic dance between Earth and Moon, a gravitational interaction that has been occurring since the Moon formed and will continue for billions of years into the future. Every incoming wave, every tide pool exposed at low tide, every ship waiting for high water to enter harbour is part of this larger story of how gravity shapes the motion of celestial bodies and how the moon, our constant companion in the night sky, continues to sculpt the behaviour of Earth's oceans through the subtle but inexorable pull of tidal forces. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath the Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice. material that spacecraft have flown through and analysed, the presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harboring biospheres in their hidden oceans. Binary star systems, where 2 stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from 2 suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets and the basic ingredients for life: elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shockwaves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Xio, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty.